For the past 70 years, researchers have been building AI systems that try to mimic human intelligence, meticulously programming them with rules and knowledge to mirror the way we think and solve problems. The idea was simple. If we could encode all the knowledge and strategies humans use into a machine, then that machine could perform tasks just as we do. From playing games like chess to diagnosing diseases, these AI systems were designed with carefully crafted rules, meant to capture human expertise and logic. But as the time went on, it became increasingly clear that this approach had its limits. These systems, while clever, were fragile. They work well in tightly controlled environments or with problems that didn't stray too far from what they were explicitly programmed to handle. A chess program could play a perfect game based on preset strategies, but falter in the face of a novel move that fell outside its encoded knowledge. The real world, with all its messiness and unpredictability, was far too complex to be fully captured by a finite set of rules. By the early 2000s, the shortcomings of this rule-based AI became undeniable. Despite decades of effort, the field struggled to produce systems that could genuinely match human versatility and adaptability. The truth was that human mind was far more complex than a series of if-then statements, and the world it navigated was far more unpredictable than the systems could manage. Enter the bitter lesson, a term coined by Richard Sutton, a prominent figure in the field of reinforcement learning and artificial intelligence. Sutton argued that the history of AI research teaches a hard truth. When it comes to creating genuinely intelligent systems, the key isn't about crafting human-like rules, and instead, it's about harnessing the power of computation and leveraging the great power of general-purpose methods, which are methods that continue to scale with increased computation. And the two methods that seem to scale arbitrarily in this way are search and learning. Sutton's bitter lesson was a stark departure from the traditional AI approaches that had dominated the field for decades. It was a critique of the methods that had led researchers to believe that they could encode the complexity of human mind into neat algorithmic boxes. Instead, Sutton emphasized the importance of embracing the raw computational power that machines offered, power that could be used to perform vast searches through potential solutions, or to learn from enormous amounts of data in ways that no human-based knowledge system could ever match. The field of chess provides a clear example of the bitter lesson in action. Early chess programs, like those in the 60s and 70s, were heavily reliant on human expertise. Programmers would encode chess strategies and heuristics, relying on human knowledge of tactics and strategies to guide the machine. These programs could perform well with the boundaries of their programming, but were often outclassed by human opponents who could think creatively and adapt to novel situations. However, with the advent of more powerful computers, a shift occurred. Instead of relying solely on human-derived rules, newer chess programs like IBM's Deep Blue began utilizing brute force search techniques. Deep Blue famously defeated world champion Garry Kasparov in 1997 by calculating millions of possible moves and counter-moves in mere seconds, something no human could match. The lesson here was that sheer computational power, coupled with the ability to search vast spaces of possibilities, proved more effective than trying to mimic human thinking. Similarly, in the realm of speech recognition, early efforts focused on rule-based systems that attempted to model human linguistic rules. These systems used handcrafted rules to parse sentences, understand grammar, and map sounds to words. However, these approaches struggle with the variability and complexity of natural speech, such as different accents, pronunciations, speaking speeds, and background noises, which were all factors that this system could not easily handle due to their rigid rule-based designs. As more data and computational resources became available, a shift to machine learning approaches transformed the field. And instead of handcrafting rules for every possible sound, researchers trained models on vast datasets of spoken language. These models learned to recognize patterns in speech that no human rule crafter could anticipate, leading to systems that could understand and transcribe spoken language with a high degree of accuracy. Leading to a system that could understand and transcribe spoken language with a high degree of accuracy. The power of this approach became evident in the dramatic success that followed. One of the most striking examples was the rise of deep learning, a technique that relied not on handcrafted rules, but on massive amounts of data and computational resources. Deep learning models demonstrated an ability to learn patterns and representations that were far more sophisticated than anything created by human-engineered rules. This shift was famously illustrated by the triumph of AlphaGo, the AI developed by DeepMind that defeated the world champion Go player Lee Sedol in 2016. Go, which is a game vastly more complex than chess, had long been considered beyond the reach of AI, precisely because its strategic depth could not be fully captured by pre-programmed rules. AlphaGo's success didn't come from a team of experts meticulously encoding Go strategies into its algorithms. Instead, it learned to play the game by training on millions of examples and exploring countless potential moves, again through the power of search and learning. In recent years, large language models, like ChatGPT, have shown remarkable abilities in understanding and generating human-like text. And again, these models are not built on carefully crafted linguistic rules or syntax trees, but on vast neural networks trained on terabytes of text data. Their architecture allows them to learn intricate patterns in language, capturing nuances, context, and meaning in ways that no rule-based system ever could. And by leveraging enormous computational power and vast datasets, these models are able to generalize from the data they are trained on, producing tests that can answer questions, write essays, and even generate creative stories. The second general point Sutton makes in The Bitter Lesson is that the contents of human minds are far too complex to replicate directly. This idea is crucial in understanding why AI has shifted away from attempting to model human thought and towards methods that leverage the strengths of the machines. Human cognition involves not only conscious reasoning and knowledge, but also a vast array of subconscious processes, emotional context, sensory integrations, and learned experiences. This richness and complexity make it impossible to capture it with a set of predefined rules, or even through an exhaustive dataset. Thus, to conclude this narrative, the evolution of AI from rigid rule-based systems to the sophisticated data-driven models of today underscores a profound shift in our understanding of intelligence and computation. Richard Sutton's Bitter Lesson illuminates this transition, revealing that the true path to creating advanced AI lies not in transferring human knowledge to machines by handcrafted rules, but in harnessing the vast capability of computation and leveraging general-purpose methods, such as search and learning, to navigate the complexities of the real world. And that's basically it for this video. I hope you found this explanation helpful, and please hit the like button if you did. Also, don't forget to subscribe if you want to stay up to date with the content I'm creating on this channel. See you next time. Bye bye!